This is session 18 for models in epidemiology and biostatistics. I am Gordon Hilton Fick. For this session, we're going to be looking at sample size. Most of you have seen at least some sample size determinations from maybe even your preparation courses you took years ago, or perhaps you saw the session on sample size and confidence interval width that I discussed in session 2. It is true that sample size is linked now by power determinations, also by confidence interval methods, and is perhaps much more recently, sample size has been explored in contexts in which the author is interested in determining sample size in such a way that the modeling they plan to do will be viable and that they have a decent chance of seeing the things that they'd like to see. Well, what I'd like to do for this particular session is look at some of the, shall we say, landmines connected with sample size determination. For many years, I gave various versions of this session in which I gave a fair bit of critical attention to a particular paper and a particular recommendation that appears to be stated within that paper. And I'll be commenting on that considerably more and doing so again for this particular session. A slightly updated version of that critical determination and critical assessment of that article. We'll also be using that article as an example of how to do a detailed statistical review of a paper in which there's models present. Then later in this session, we'll be looking at some comparatively recent articles that really do get at what appears to be, at least in present time, the most viable way to at least plan some sample size issues when there is interest in modeling and modeling strategies. So that's the plan for this particular session. I'm going to begin with an example of an article. Actually, it was a research protocol that I had an opportunity to review. This is from some years ago, but it will work for us for the purpose that I have for you. So why am I doing that? Well, this particular research protocol gave a very small sample size calculation determination as a part of the protocol. And that should raise serious concerns whenever the number is small, because at the very least, the authors should have been using methods that address the small sample size and not using large sample methods and then getting a small number. So this is the intention of the time I want to give to this particular session. So within this protocol, which by the way was not recommended for funding, they came up with a sample size of 11, and they claimed to have 80% power to show what they said was an observed response of 10% being significantly different from a portion of 0.1%, representing no effect. Even that's confused to read it. Nevertheless, if one proceeds and has a look, you could say, well, how would they have possibly gotten a number of 11? And so what I'm going to show you is one way in which they may have come up with the number 11, and then I'm going to offer some critique of that number. So if in fact the authors used the sampsci command in Stata with the following command that I'm showing you here, this particular command, it does indeed report a sample size of 11. And so you might be thinking, well, that sounds pretty good. And they have an alpha of 0.05, a power of 80%. What does that really entail? Well, let's have a look. So a possible way of reviewing that confusing sentence that the authors presented here was that they wished to test a small null hypothesis of 0.1%. That would be this number here. Okay, and then wanting to see an alternative of 10%. So, well, that would be something around where they say observe response of 10%. Well, maybe. Nevertheless, if you do that, if you put in a null hypothesis of 0.1% and then an alternative of 10% with the sort of somewhat standardized alpha of two-sided 5%, power of 80%, you get this number reported by Stata of 11. But this is based on, but if you review the techniques used by Stata and the sampsci command, you can see that it was based on the normal approximation to the binomial. Oh my. And in fact, in both cases, the null hypothesis and the alternative hypothesis, the exact binomial distribution is not it's not a symmetrical distribution. It is certainly miles away from being even close to a normal distribution. Let's look at this in a little more detail, just to get a sense of the difference here between power and size and so on, with distributions that are very clearly not symmetrical. And you can do that quite nicely in Stata. It's not that hard to do. The generate command provides all that we need, along with binomial p and binomial tail, to give us the actual probabilities and the tail probabilities that one might consider. For example, the null hypothesis distribution, the alternative hypothesis distribution, and you'll see I'm including another one here of 14% just for illustration. All right. So if we then give these commands to Stata and then look at a list, we do in fact get a pretty simple looking set of, here are the probability distributions, and here are the tail probabilities. Let's look at this in a little bit of detail. For example, we might ask, if in fact we were to wish to test a null hypothesis of that very small p equals 0.001, then we could ask, is there a rejection rule that we could formulate that might achieve something close to the 5% that we wanted, where alpha should be 5%. Let's have a look. You can see that, in fact, if in fact the null hypothesis is true, the probability that we get 0 responses is overwhelming. Not too surprising, right? It's a very tiny probability under the null hypothesis. And that we see that with 1, the y equals 1 is a small number, the y equals 2 is even tinier, and then the distribution is essentially nearly 0. So how could we construct a possible rejection rule if indeed our role was to try to get a power determination here? Okay, well let's give this a look. Let's suppose that we were to consider a decision rule that would be to reject H naught if y is greater than 0. Okay, well, we can see that that particular probability of y being 1 or more, you can see, is given by this number 0.0109 and so on. Right, so we can get that from the either adding together the probability of anything other than 0 here. And then we get that in fact, if we were to use such a rule, we get an alpha that's less than 5%. Now, there is no rule. There is no rule that has any higher alpha in this particular case. In other words, well, we either reject if y is greater than 0, which means anything except 0, or there is no other possibility here, right? So, what does that mean? What would the power associated with such a decision rule be, the actual power be, if we were to use this particular decision rule? That is, what's the probability we reject if indeed the probability under the null hypothesis is 10%? And in fact, it turns out that turns out to be 68.62%, not 80%, right? It's not 80%. And where would we see that? Well, we could calculate that from this particular tail area right here that Stata nicely reports for us. There it is, the 0.68661 and so on. So you can see that even though Stata said we got 80% power and an alpha of 0.05, in fact, the only rule that has any possibly sensible power here, or a sensible size here, has alpha that's less than 5%, but you can't have anything higher. There isn't anything, and the power is not 80%. It turns out that if we were to explore a variety of other null hypotheses, for example, if we had raised the probability under the alternative to as high as 14%, then we do get a number that has 80% power. So the point here being is that Stata's algorithm is reporting a number, but it always requires, and I guess the key message for you from this is that if a sample size determination gives a small number, get suspicious. Check to see what methods are being used in order to determine this sample size. And you can see here that we're in trouble. Okay, another part to this that I would encourage all people to do when they're considering the implications of a sample size is to look at the possible confidence intervals one might see. And well, the number of options here turns out to be comparatively small. If in fact we were to consider the sample sizes or confidence intervals with a sample size only of 11 here, then we see that, well, I mean, we could get an observed y of 0. And then if we use Stata's confidence interval immediate, well, what do we see? We get this confidence interval. It's a one-sided confidence interval. In fact, perhaps you've seen some of this. When there really is only one side, to a confidence interval, then it's really a one-sided interval, even though you may have requested two-sided. All right. Now we can also see then, if we were to have obtained, if we were to consider the possibility of getting a response of 1, then we get this confidence interval. Again, a very wide range, right? Because the sample size is only 11. This is a wide interval, right? Very wide interval. Not too surprising, right? So the null hypothesis that that these authors were supposedly contemplating was a very tiny number. But notice, even if they were to get nobody, in other words, the response was 0, the confidence interval here is very wide. Similarly, with other possible outcomes, sample size of only 11 yields extremely wide limits. And notice here the lower limit allows for very low values of p, but unfortunately, the confidence intervals are so wide that you could say, are we really getting anything of any real value here? Okay. One very nice picture that I am including in these slides is taken from the very fine book by Ramsey and Schaefer called Statistical Sleuth. And they offer for your consideration the implications of a confidence interval in an actual situation. So let's retrace what we've just done with that previous example with a very small null hypothesis and alternatives that might be quite a bit higher, and in which the larger is clearly perhaps anticipated here. So what have we got? We've got a null hypothesis that's down here, perhaps that very small number that we saw earlier. And then we've got values that are practically significant, perhaps the numbers like 10% or higher. Remember, we had the 10% or the 14%. All possibles. What are the confidence interval possibilities we might be considering here? All right, well, let's take a look. We could see that if we got a confidence interval like illustration or example A, we can see that it is consistent with practically significant alternatives and not with the null hypothesis, right? So an interval range that does not include the null, but does include practically significant alternative values, is one like that. Another option, option B, is one that is consistent with the null hypothesis, right? The confidence interval includes the null, and, well, a quite wide range of values, but none of them that are in the practical range, okay? Notice type C here. The data are neither consistent with the null hypothesis or with practically significant alternatives. Now, this is one that sometimes experimenters or investigators grapple with. They get a confidence interval that doesn't really help. It leaves them in a never land. So interval D is narrow, that's fine. Doesn't include the null, well, that might be helpful, but doesn't also include the values that are going to be helpful to the investigator. So confidence interval width can be a double-edged sword here. Here's the last example where the confidence interval is so wide as to be of no value at all. It's consistent with the null, yep, but then it's also consistent with practically any other value. So again, that's the small sample size situation. Here's maybe a large sample size situation, but we're still kind of in trouble. You might then speculate that wouldn't it be nice if we saw example A or example B most of the time, but that's not always the case. All right. So now we come to the issue of sample size when modeling is planned. So there's a number of challenges here. You could say, well, the usual methodology that I have offered to you so far is the methods based on power, which again can be looked up and can be read about in either Stata or the R help files, and also my suggestion that confidence intervals and confidence interval widths ought really to be involved in the determination of sample size. But maybe the most crucial these days is that the authors plan to do some modeling. They may even have a candidate model in mind. They may have anticipating a particular circumstance that's going to be helpful to them. Now, there was in the mid-1990s a paper published, and I'll show it to you in a moment. And it really, well, it was quoted a lot. And there were many, many articles published in which authors offered their sample size section in their protocol using the Peduzzi paper. And so what I'm going to do now is offer a critical review of the Peduzzi paper. Back when I was teaching this particular course, what I would actually do is ask the participants in the course, the students in the class, to read this Peduzzi paper, not the more technical parts to it, but the more application-oriented parts to it, and address issues like, well, the main messages, and, well, the fact that this quantity called the event per variable, or event per covariate, really caught on with investigators. This EPV, events per variable, characteristic really caught on, and magically this number 10 became the characteristic that was so widely quoted by so many authors. So what I invited the participants in my class to do is to read the paper and ask, did the authors actually make a strong case for this EPV of 10? They also offer some of the rationale that they appear to offer as indicating the rationale for a particular, for various values of EPV. A bit of a more technical side to this paper. I'm going to show you the paper in a second. They offer regression coefficient estimates, p-values based on the Wald test, and in their particular case, a model that had 6 indicator explanatory variables and 1 explanatory variable with 3 levels. So that in fact, there's 192 possible rates to study in this particular investigation. To my understanding, the actual data set that Peduzzi et al. Used to construct all of this has never been made available. So we're going to have to be offering some cautious interpretations. But I think with what they've given us, we're going to be able to see quite a lot. Okay, so here's the paper. Very distinguished set of authors, most notably perhaps Alvin Feinstein, the senior author on this article, published in the Journal of Clinical Epidemiology back in 1996. And as I mentioned, this particular article received a huge number of citations. And you'll see here that they say, for EPV values of 10 or greater, no major problems occurred. But what was that actually based on? Well, they did see problems if the EPV values were less than 10. But again, what was that all about? Let's try and give this a fairly critical assessment. They say they performed a Monte Carlo study. Well, it's certainly a quite unusual simulation, quite unusual study to be called a Monte Carlo study, and I'll comment on that as we move forward. They did come up with a methodology for constructing data sets with various EPVs. Again, the methodology behind how they constructed these data sets, a little bit technical and maybe a little outside of where we're going to go. They used a Bayesian argument. The Bayesian argument here, though, in a frankly rather unusual way, and far from the standard way in which we see Bayes being used. But you can see here that they do say that EPV values of 10 or greater, no major problems occurred. And that's where the number 10 kind of caught on. They looked at 2, 5 and said they were unacceptable, and then 10 and higher, and then said they seemed acceptable. Okay, so that's the background here. So the participants in this particular session of my class, then we're challenged with, does this paper really justify the implications? And let's take a look. So as I mentioned, in the actual course that was offered, this ended up being a fairly freewheeling set of commentary from the participants in the class, and many people offering criticism. However, as I said, this became for a period of time the article to quote if you were going to be using models. All right, let's look at this in a little more detail now. So the actual data came from a cardiac trial, the Department of Veteran Affairs Cooperative Study of Coronary Artery Surgery. Okay, so these are pretty seriously ill people. There were 686 participants in this study. The authors elected to use only those participants that had what they referred to as complete data here. There was no attempt at any attempt at imputation. That's way down the list of concerns. And well, as one might well gather, these were quite sick individuals. There were 252 deaths, the event of interest here, in the first 10 years of follow-up. And so there were 421 survivors. And that, just to remind you, we're excluding those that did not have the data that was needed for this modeling assessment. Now, they then said that, well, 7 variables were considered, here I'll use their term, cogent predictors of mortality. Okay. And they then argued that the choice of these 7 variables were based on univariate tests. Well, you do see that as an argument, and how you come up with the variables for analysis is a tough one. That it's based on univariate tests is widely criticized, and I've discussed and commented on this a lot earlier. So in this particular case, since there were 252 events, and there were 7 explanatory variables given here, right? They had the variables I'm going to show you in a second here. The events per variable characteristic here was 36. Okay. Here's the list of those 7 variables that were considered. And I've just used abbreviations for them. S, H, N, C, D, V, and A. Now, they're fairly, so all but V were indicator variables, in the first case, for example, for depression. And there you can see the number of individuals that were given a classification of depression I've included here. The variable V, though, was not an indicator, but in fact was something called the number of vessels diseased. And there were 3 values for V, 1, 2, or 3. Okay. Then the authors presented the model based on the actual 673 participants. And there's the model that they fit. Okay, let's have a little look at this. This is the log of the odds of mortality being this set of 8 terms, a constant term, and then these 7 further terms. The first thing you will note is that this model is additive. There are no terms involving products here. Now, it would be also important to note that these 7 explanatory variables were not mutually exclusive. So this was an additive model using non-mutually exclusive explanatory variables. In previous sessions, we've looked at how to interpret the regression coefficients from a model that's based on strictly terms that are additive. So what have we got? We've got the model here, and this is something that I strongly encourage that people do when they're reading a paper. Do you have enough information when you're reading a paper to see what model was actually considered? And did they give you the fit? Here's the fit. Here I'm using the Latin equivalent of the Greek letters and the actual values of the fit, right? In other words, we would have had available to us the fitted values for each of the 673 people. And they also report the standard errors associated with each of these regression coefficient estimates. So as I mentioned, the model was additive. And as we've seen in earlier sessions in this series, each coefficient requires the phrase assumed common to all the others. Let's look at a couple of examples. Let's take H, the hypertension characteristic. Beta 2 here. What is beta 2? Well, it's the log odds of mortality for those with hypertension minus the log odds of mortality for those without hypertension. But this difference here is assumed common to each combination of the presence, or absence of all the other explanatory variables. In other words, beta 2 here applies to both the depressed group and the non-depressed group. It applies to those who have this NYHA classification or not. It applies to the set of individuals that did have a history of CHF or not. It applied to both the diabetics and the non-diabetics. So notice this issue about hypertension here, this beta 2 number, is a rather rarefied comparison. It's a comparison between 2 log odds of mortality, but it refers to a wide range of differing groups. Is that at all plausible? Is it's sensible to think of hypertension as an explanatory variable, and a single explanatory variable applying to essentially all combinations of all sets of the other variables. Okay. So what can we see about this number, 0.52? Well, it's an estimate of that assumed common difference between two log odds. Yes, indeed. There's the standard error, so you can see that this number is giving us a suggestion of beta 2 being meaningfully different from 0. Right? Because if I were to subtract 2 standard errors from 0.52, I get something that's larger than 0. Okay, but I remember, though, that these regression coefficient estimates require this rather elaborate assumed common interpretation in each case. All right, let's take another look at another example. How about beta 2 and beta 3? What are beta 2 and beta 3 here? Well, beta 2 and beta 3 and beta 4, refer to this characteristic N and the characteristic C. Let's look at N and C here. From the full or so-called actual data set of 673, these two explanatory variables have regression coefficients that could include the null. Right? The standard error here is quite large relative to the size of the estimate of the regression coefficient. Same thing with C. So that means that these two numbers, beta 3 and beta 4, could possibly be 0. That they're not, even with the full data set or the actual data set, beta 3 and beta 4, even though they'd argued for their inclusion in this model, they apparently, many authors would say, if this is where I am in my modeling strategy, why am I including those two explanatory variables, N and C? Now, the interpretation of beta 6 even gets more complicated here, because, as I mentioned, V is not an indicator variable. V takes on the values 1, 2, and 3. Now, notice that beta 6 is, in fact, a difference between the log of the odds of mortality, comparing those with a V of 2, that is the number of vessels being 2, and the number of vessels being 1. Okay, so that is an interpretation of beta 6. It is the log odds of mortality for those with V of 2 minus the log odds of mortality for those with V of 1, assumed common to all 6 of the other explanatory variables. Further, and this is not at all obvious, maybe when you first look at this, but notice it's also a difference between two log odds of mortality, that is, the log odds of mortality when V is 3 and the log odds of mortality when V is 2. Right? The difference is 1. So what that means is that beta 6 is not only assumed common to all the other explanatory variables, but it applies to both V equals 2 and V equals 1, and it applies to V equals 3 and V equals 2. What's the rationale for that? It's an assumption implicit in the use of this model, isn't it? Yuck. Yeah, that's not at all helpful, is it? And you would maybe also notice that twice beta 6 is the log odds of mortality for the vessel equals 3 and vessel equals 1. Oh my goodness. Okay. So, needless to say, almost all of this paper is based around the fit that I have presented you with up here. This fit is becomes the basis for the rest of their analysis. It's not the actual population characteristics here, but in fact, the authors then inextricably treat the estimates here, these B naughts, B1, BI, and so on, as somehow givens for reasons that are, again, way, way, way from being clear. Okay. What's going on here, you're thinking? Well, because what they then did is generate samples of the covariate patterns using techniques that are, again, a little bit elaborate to generate data sets that, instead of having the EPV of 36 they had with all 673 actuals, they got pseudo data sets, or fake data sets, frankly, with various EPVs. And again, the technology behind that is interesting, but we get no indication of the actual number of distinct covariate patterns. That's not included in this article. So we're kind of in a little bit of a quandary here. Again, we did not have access to the actual data here. And the algorithm for the generation of these samples is interesting. For those of you who have an interest in Bayes, you may find this part of the article technically rather interesting, but it's miles away from the issues at hand, because the authors proceed to take the estimates obtained from the actual data set and then, in a curious way, view them as population characteristics. And by the way, I would remind you that the confidence intervals for each of these actual explanatory variables had a wide range of values. Okay. Because the the authors here are offering these regression coefficients as the basis for assessment, even though they're far from sort of definitive in any sense, even though they were based on a fairly large number of a sample size of 673 here. Okay. Now, the argument that's offered is that if your role in using a model is for one of prediction, that somehow magically we're supposed to come up with this EPV as being the key to all of this. But is it? Almost all of the article turns out to be about the various regression coefficients and how close the regression coefficients from the simulated samples with the various EP values come to the regression coefficient estimates B1 to B7. In other words, the article is about the regression coefficients and their somewhat troubling interpretations, as I've discussed, and not really about prediction at all. Another problem. So the authors argue that the very low EP values give problems, yes, and they do detail issues when the EPV values are really low, that they get models that don't converge or very, very poorly constructed confidence limits and or estimates. And then, well, if you read this article, somehow 10 is viewed as important here. I would say that over the years that I have been reviewing this particular article with fellow students and colleagues, the number 10 just seems to come out of nowhere, really. It is, and even in fact, the authors seem very, shall we say, cautious in their use of this number 10. Nevertheless, the number 10 is what ends up being cited almost all the time in the research literature, at least until comparatively recently, and I'll be coming to this in a minute. Now, it would have been of interest for me and for many over the years to have tried other models with this data set, but I regret to say that for unknown reasons, that data has never become available. And you could say it would have even been helpful to have seen some 2x2 tables with each of the explanatory variables. That 2x3 table for the vessel variable would have been of interest, but to no avail. So we have, I would argue, a pretty serious critical review of that article. And somewhat disturbingly, for a time, this article being so widely quoted, and even though it would appear at least that almost no one was actually reading this article with some due diligence. Can't say either way that I know about that. So what have I been offering to my colleagues and students as the options here? Well, most of the time I would still go back, even though modeling was being considered for a particular project, that colleagues consider 2x2 tables first. Consider the 2x2s and or perhaps some larger tables. Here I'm focusing my attention on when the outcome is binary. There's quite a bit about these matters if the outcome is of other types, and that we'll leave for the time being. But oftentimes I have found over the years that when an investigator looks at, for example, a 2x2 table or a series of them, and then looks at the numbers that are needed for that 2x2 table to yield viable estimates of, for example, odds ratios, that gives you at least the starting point for consideration of sample size. Now, it's true that there are and continue to be quite a bit written about how to construct sample size estimates based on power when there's modeling being used. My own impression is that is not widely used because of the challenge being around the fact that there's so many characteristics that an investigator won't know with any kind of authority at the design stage, and yet you need these numbers in order to consider sample size determination. All right, so now let's take a look at what are some interesting advances that have been made in recent years, within the last 5 years actually, of how to handle sample size when one have models in mind. Well, let's review a few of the issues then before we look at some of the details behind these recent publications. So you've got, for our purposes then, a binary or dichotomous explanatory variable. Outcome variable. The health outcome, the response variable being binary. That is disease, non-diseased, remission, non-remission, and so on. Then you have the determination of the explanatory variables that you wish to explore, and those include variables, the exposure variable that's of primary interest, or there may be more than one. There may be If there's more than one exposure variable, are the exposure variables being considered with the possibility that their implication for the response is that they may involve interactions. In other words, the effect of one exposure variable, or the impact of one exposure variable, might depend on the level of the other exposure variable. Then we have, in addition to exposure or exposures and the possibility of interaction, we have a listing of the potential modifiers and potential confounders, ones that could be well articulated in the research literature or maybe still very speculative. We might just have other explanatory variables that we just need to include in the models, and we've seen some examples of that, where an explanatory variable might not be either a confounder or a modifier, but it is clearly involved in an understanding the relationship between the disease or the outcome and the exposure or exposures. We need to also have in mind whether or not variables that are measured, explanatory variables that are measured, might well influence the outcome in a way that is nonlinear. And you can see that we've seen from that it may be more than one explanatory variable will be needed to handle the nonlinearity. We may well need terms to handle linear and quadratic, or maybe we might well have the equivalent of a piecewise linear function, or possibly even one of the splines that we've seen. Okay, what are we getting at here? We're already looking at the potential for a large number of explanatory variables on the right-hand side of the regression equation. As soon as we've addressed the exposure or exposures, the modifiers, confounders, or even just a list of possible explanatory variables, the numbers get large. It might well be that we're faced with a large number of regression coefficients. I think it's fair to say that within the epidemiologic paradigm, as I have attempted to articulate in this session and in earlier sessions, it typically involves beginning with models that are the most complicated, and then using modeling strategies to attempt to simplify the model and simplify it in a way that does not lead us to oversimplification or the missing out on key characteristics. Some of you will know that the strategy of starting big and then reducing to small is sometimes called backward elimination. I don't know that I like using that name, but well, that's just what we're faced with. But in any case, it means that if we really are serious about wanting to be able to assess that initial, quite complex scenario to begin with, then, well, I guess we need a sample size that, i.e. number of participants, that will address all of the potential exposures and other variables and this complicated model right at the start. It might well be that very first step with that complicated model is one that determines the sample size you're really going to have to go after. Right. And so for many investigators, this becomes a quandary, right? It's like I want to start big. I think that a lot of things may be in play, and maybe there's going to be a complex interpretation that will be the most important finding in the paper. But am I going to have any chance at all of addressing that complicated situation? Right. So as I mentioned, perhaps it is still going, even notwithstanding the new methods I'm going to mention to you coming up now, it may still be important for you as when you're beginning to explore this to start with sample size considerations that are very simple. Maybe set up some 2x2 tables. Maybe that confidence interval approach will be needed. And then maybe you're going to be able to address, or at least have a pretty good idea of what the overall or marginal prevalence would be for the health outcome that's being studied. So as I mentioned, back in the 1990s, papers were suggesting this notion of events per variable. Much more recently, authors are suggesting that maybe the better term should be events per parameter, because we might well have, as I've mentioned, a circumstance in which we need, for example, terms to address modification and or interaction, which involves additional parameters in the right-hand side of the regression equation. And and we might well have issues of nonlinearity again, where we're going to have additional parameters on the right-hand side. So events per parameter, you might think then, being really the issue. And it is also widely noted that that the study or the estimation and critique of some parameters may be harder to do than others. It's widely noted that the assessment of modification and or interaction or nonlinearity can be harder to see than some of the simpler circumstances. Okay. Well, it turns out that the area under the curve is now getting another look from the point of view of sample size and the notion of the R-squared or pseudo R-squareds that are often seen in logistic regression, for example. It's been determined fairly recently that the AUC and these pseudo R-squares are actually quite close relatives and addressing the issue of sample size determination in quite comparable ways. And there's been some articles written about that too. So then how do we incorporate the AUC and or the pseudo R-squared into statements that we wish to make about prediction and or the effective study of a model and the modeling process that we have in mind? Well, it turns out that it is regarded as better to use all of the available data for model development. In other words, data splitting is now becoming a matter that is being viewed with considerable concern these days, and that there are alternatives to data splitting, such as bootstrapping, that can require that can assist us in this endeavor, rather than from the outset planning to have to split the data for model development. Needless to say, data splitting involves larger sample size numbers as well. So what have we got? Well, it turns out that there are characteristics that are now being viewed as the crucial things to use when one wishes to do sample size determination. You want to minimize the potential for model overfitting. You want the estimates of the model's parameter to be meaningful, and we want the other characteristics of the model to be studied with clarity and confidence. So it turns out that this sample size process is now widely seen in the research literature as a 4-step procedure. Now I'm not proposing to go through all of the details involved in this particular process. And I'll explain why in a minute. So the first thing is that although I've restricted my attention to dichotomous health outcomes, this methodology that is now becoming available applies also to measured outcomes, to time to event outcomes, and other combinations of characteristics too. There's an article where the first author is Riley, that was published in BMJ, that gives a very fine overview to this. And what I'm coming to, I guess, is maybe the most crucial thing for you now at this particular stage in this session, is that quite recently the key investigators, Riley, and there are other important names, I'll be showing you the list in a minute, have developed a package called PM sample size, so prediction model sample size. They have a package in R, and they also have an ADU for Stata that is available. And the paper, and this research literature is changing quite rapidly, thanks to the key authors. Here's a little bit of the nitty-gritty for you then. For Stata, once you have obtained the crucial files, the do file and the help file, you add those files to your personal do directory in Stata. And for example, in my MacBook, the personal do directory is in this place. But what you can do within Stata is determine where the ADU path, with the ADU path command, you can find where the files need to be placed. And here's an example in Stata of how to use PM sample size with the type B for binomial or binary, and the specification of a pseudo R squared, the number of parameters being contemplated, and the prevalence overall of the health outcome. And we have almost exactly the same format in R, where one gives the you get the package first, and install the package, and then add it to the library, and then the command is essentially the same. You give a B for binary outcome, R squared value, a number of parameters, and a marginal prevalence estimate for the health outcome being considered here. Okay, here is a list then of a few of the key papers, the key papers that have been written about this recently. Richard Riley involved, Frank Harrell, and other players. And you can see that there's quite a few of them. I'm just to quickly show you. Suffice to say that these papers may be game changers for the determination of sample size when one is modeling. And you will see that per se these commands do not require the EPV. However, if you look at some of the illustrations in these articles, all of them will show you what the EPV would be. It's pretty clear, right? Here we can see here that it wouldn't be so hard to determine what the EPV will be for these settings. Again, this is a little bit on the technical side. However, as of my most recent investigations, I think these are the methodologies that deserve consideration. just to wrap up this session then, do keep in mind that if you appear to be getting numbers that seem unrealistically small, you're going to have to again take into consideration that these calculations are based on so-called asymptotics. Okay, you're going to have in mind that these characteristics you shouldn't be getting small numbers. Even though you'd love to get them, you're not. Now, I should also mention again that there is a way, instead of giving r squared here, you can give the AUC value and that you are anticipating. And there's quite a bit of literature on this as well.